Alright, section 6.4 is going to be the last section that we'll cover in the course. I'll probably split this section into two videos, but the main topic is called matrices. Now, the main topic for chapter 6 is systems of linear equations, and we've looked at three methods for solving a system so far. They were the graphing method, the substitution method, and the elimination method. Matrices would be the fourth method to know. There's a definition that says that a matrix, or sometimes a coefficient matrix, that means the same thing, is a table of numbers arranged in rows and columns. The plural of a matrix is matrices, okay? And that's what the section is called. Here's how we denote a matrix. Usually we use a capital letter to denote a matrix. I suppose that you could call a matrix anything that you want, but most books will use capital letters there. And you got this table of numbers arranged in rows and columns, and we usually use like square brackets, or sometimes there's rounded brackets to enclose all the numbers in the table. Okay. One of the things that we sometimes care about is the size of the matrix. The size of the matrix is characterized by the number of rows and the number of columns, and it's got to be in that order. Okay, so matrix A would be a 2 by 2 matrix. There's 2 rows and 2 columns. Here I've got some other matrices written, and I've got the size of each matrix written below. So matrix B is a 3 by 2 matrix because there are 3 rows and 2 columns. Matrix C would be a 2 by 3 matrix because there's 2 rows and 3 columns. Matrix D would be a 1 by 2 matrix because there's only 1 row and there's 2 columns. It's always the number of rows first and the number of columns second. Okay. Now, why do we have matrices? Well, the topic is systems of equations. And here's a definition. An augmented matrix can be used to represent a system of linear equations. Here's an example. Suppose that we have this system of linear equations, and I'm going to write this as an augmented matrix. Well, let's see here. So the rows are going to be represented by the equations that are given. Here I've got 2 equations, so I'm going to have 2 rows. The columns are represented by the coefficients that are in front of each of the variables. Okay, so like in the first row, I've got a 7 in front of x, a 1 in front of y, and then I've got a -6 in what's called the coefficient column. In the second row, I've got a -2 in front of x, a 13 in front of y, and then a 5 in the coefficient column. Now, notice that in an augmented matrix, I got this vertical bar drawn. Now, that's a necessary thing to have. If you don't have the vertical, and by the way, the vertical bar represents the equal signs there that would be in this system. We don't write equal signs in a matrix. We use this vertical bar instead. Okay, it's a notational deal. But if I didn't write that vertical bar, then it would be understood as a coefficient matrix. Okay, a matrix or a coefficient matrix is just a table of numbers arranged in rows and columns. A coefficient matrix has no direct connection to a system. Okay, it's just a table of numbers. So in order to represent a system, okay, we're using an augmented matrix. Right, now the topic in chapter 6 is systems of linear equations. So when we talk about the topic of matrices, more specifically, we're talking about augmented matrices. Okay, so there's a difference between an augmented matrix and just a coefficient matrix. Here's another example. Okay, I've got this system of linear equations. I'm going to write it as an augmented matrix. I've got 3 equations, so I'll have 3 rows. And in the top row, I've got a 1 in front of x, a 3 in front of y, a 2 in front of z, and a -1 in the coefficient column. In the second row, I've got a 2 in front of x, a 5 in front of y, a -1 in front of z, and a 2 in the coefficient column. In the third equation, I've got a 3 in front of x, a -8 in front of y, a 0 in front of z, since I don't have any z's, And if I subtract 4 from both sides, negative 3 minus 4 is negative 7 would be in the coefficient column. In other words, equation 3 was written in an unsimplified form. So some students would make the mistake they'd put a 4 here in this spot. You don't want to do that because we don't have any z terms. Okay. The point would be, of course, to have you guys see that when you're picking off the coefficients to form the matrix, make sure that the equation is in a simplified form beforehand. Okay, here equation 3 was not simplified. And let's go the other way. Okay, what if we had an augmented matrix? Let's write it as a system. Okay, here's one example. So here's my augmented matrix. I'm going to have two equations, and there's going to be two unknowns. The top equation, I've got a 5 in front of x, this will be a 5x, and then a minus 3y equals 4. And then the bottom equation, negative x plus 4/3 y is equal to negative 6. Okay, and then here's another example. I'm going to have three equations with three unknowns. I'll call them x, y, and z. So my top equation is going to be 2x minus 7y minus z equals 0. The second equation is 3y plus z equals negative 1. And the third equation is negative 5x plus 9z equals 3. Okay, now the next thing that we'll want to know how to do here is we'll want to know how to compute row operations on a matrix. There are three basic row operations that you can do on a matrix. Okay, the first operation that you can do is you can switch any two rows. Now, an augmented matrix is representing a system of equations. So if you think of this as a system, you can switch any two equations that you want. That's not going to matter, right? Like, we don't care about the order of the equations that are in a group. So the same deal here. Like, we wouldn't care about the order of the rows that would be in the matrix. Number two, we can replace a row by a non-zero multiple of that row. In other words, in an equation, you can multiply both sides by a number as long as it's not 0, right? Because if you multiply both sides of an equation by 0, you're going to have 0 equals 0, and that doesn't help you in the problem. Number three, replace a row by the sum or difference of that row and a constant non-zero multiple of another row. Okay, so basically what I'm saying here in the third item is that you can use the elimination method. Item 3 is exactly the elimination method, right? What do you do with the elimination method? You're adding equations together, so hence the term sum. Sometimes you got to use a multiplier, right? You're using a constant non-zero multiple of another row, okay? And so that's how you eliminate a variable, right? Is by adding these equations together with some multiples. All right, so these are the three basic row operations that we're allowed to perform on a matrix. Okay, let me go through an example here. So in this notation that I'll be using, a capital R is going to represent a new row and a little r is going to represent an old row. Okay, now I've got this augmented matrix, and I'm going to get a new row 2, and I'm going to get that new row 2 by using the row operation row 2 equals negative 3 times row 1 plus row 2. Now, I'm going to form a new augmented matrix. Row 1 is going to stay the same as it was before, and like I said, I'm going to get a new row 2. I need to take negative 3 times row 1 plus row 2. Okay, let me do that now. Negative 3 times 1 is negative 3, plus 3 is 0. In the second column, negative 3 times negative 2 is 6, plus negative 5 is 1. And then in the last column here, negative 3 times 2 is negative 6, plus 9 is 3. And so here would be my new augmented matrix. Now, when we solve a system using matrices, we're going to have to come up with these row operations on our own. Okay, like they're not going to tell us this. That's something that we'll have to think about in the problem, and you'll see me doing that later. Here's a definition. A matrix is in what's called row echelon form. REF means row echelon form. When three things happen. Item 1, any rows of all zeros are at the bottom. Okay, I know that one of my row operations says that I can switch any two rows, so if in the calculation I end up getting a row of all zeros, I'll stick that at the bottom of the matrix. Item 2, the first entry from the left in each non-zero row has to be a 1. Okay, if you scan from left to right. Item 3, each leading 1 is to the right of all leading ones in the rows above it. So if you have a row where the first number, if it's not 0, is 1, then any row right above it has to have a 1 that would be to the left of that number. Okay. Here's some examples of some augmented matrices that would be in row echelon form. Okay. Basically, to kind of summarize what it means to be in row echelon form is you're looking for ones down the diagonal of the matrix and then zeros in the lower triangular part. Okay. Now, these other two examples would also, technically be in row echelon form, even though we don't have ones down the diagonal. All right. The three conditions are still satisfied. You got a row of all zeros, that's at the bottom. The first entry from the left is going to be a 1 here. Each leading 1 is to the right of all leading ones in the rows above it. Okay, like this 1 is to the right of this one. This 1 is to the right of this one. This 1 is to the right of either one of these ones here. Okay. So that's what we're looking for. Now, when we solve a system using matrices, we're using what's called the Gaussian elimination method, and the object is to get the augmented matrix into row echelon form by using our row operations up here. Okay, so again, we're looking for ones down the diagonal and zeros in the lower triangular part, although there are some exceptions. I'm going to stop the video right here.